Alright, so we're going to talk about the going off on a tangent theory. Have you ever heard of someone going off on a tangent?
Mm-hmm.
Like they're talking and talking, all of a sudden, whoo, she went way off on a tangent. Well, here's an example. Going around in a circle, and all of a sudden, boom, someone goes off on a tangent. This is your tangent line. From this point on this curve, this is the slope of the line at this point on the curve. Tangent lines only touch the curve one time. They only touch it, they do not intersect it. Okay, so the concept of the derivative, or the definition of the derivative is, feel free to take notes if you would like, the derivative of a function is the limit as h approaches 0 f of x plus h minus f of x all over h. And that looks super scary right now, but it'll make sense in a little bit. So, this is the derivative, and this is the process of finding it. Alright, so we're kind of going to make a tie between the definition of this derivative using the slopes of tangent lines. So we have a graph of a curve, and we have any arbitrary point x. It could be anywhere on the curve. So here's your x. The tangent line is the slope of that point right there. So this is the tangent line. Okay, I'm going to put these 3 points up here for later. Okay, so for like my roller coaster example that I used earlier, picture yourself riding on the roller coaster, and your tangent line is the person's line of sight on the roller coaster car. So if you're at the very, very, very tippy top of the roller coaster, your line of sight is going to be horizontal. And what is the slope of a horizontal line? 0, correct. And then if you're on your way down, the slope's going to be negative, and so on and so forth. So how can we find the slope of that tangent line? What do you need when you find the slope of a line? Do you remember?
X and Y.
You need x and y. Can you find the slope of a line with only 1 point?
No.
No.
You need 2 points, right?
Yep.
So we're going to talk about secant lines. We can find any other point on this curve. You can pick any other point and can draw a line between those 2 points. So we're going to choose this point up here. Okay. You can find the slope of that line, but as you can tell, it's very, very different from this tangent line. So that's probably not a very good approximation to the slope of this tangent line. That is what the derivative is, to find the slope of the tangent line at that point. So you can find, you want to find a point that's closer and closer and closer to that point x to get the line to resemble that tangent line. So you can draw this secant line, and then this secant line, and as you can tell, they're starting to resemble that tangent line more and more. Okay, so this is kind of where our key idea comes in. The slope of the tangent line is the limit of the slopes of these secant lines. Alright, so we are going to redraw this graph, the same thing, make it look a little bit nicer. The same point x. Oops. And the tangent line at that point. Okay. And like we said, we need 2 points to find the slope of a line. So we're going to pick the point out here. Well, first of all, let's label these coordinates. Coordinates are like addresses, they need an address. So what is this point right here? if this line is y equals. If this point was x, does anyone know what the y coordinate is? This is kind of, the y coordinate is f of x. Because if you have the equation f of x equals x plus 1, whatever x is, you plug that in for x. So f of 1 equals, you put in 1 for x.
1 plus 1.
So that's 2, right?
Oh, yeah.
Okay. So if you put in x in f of x, the y coordinate is simply just f of x. So these 2 points are x, f of x. And we're going to label this point h. And then the distance between these 2 points is going to be x plus h. So this point up here is x plus h. And then what would the y coordinate be? If this is x, f of x, this is x plus h, f of x plus h, right?
Mm-hmm.
Okay. And we can use this definition to find those closer approximations of the slope of the tangent line. So what we're going to do is find the derivative. So we're going to say, we're going to find the changes in the y's over the changes in the x's. So you have the change in the y, f of x plus h, minus this y, y1, all over the changes in the x's, which is just x plus h minus x, which is eventually going to cancel out your x, which simply just leaves h on the bottom. So that's how you calculate the derivative. So let's do one example. Alright, so we have the equation f of x equals x squared. If you can recall, that equation looks like, the graph of that equation looks like this. Okay, but the graph is not important at this point. So you're going to use this to find the derivative of this equation. So like before, I had f of x plus h minus f of x, because my coordinates over here were x. Let's see how many it is. Okay. You want to plug this x plus h in for here. So let me just show you how this goes. F of, you're going to plug x plus h into here, squared, minus your f of x, which is just x squared, all over h. And this is as h goes to 0. That's not there. Okay, so then if you do foiling, do you remember how to foil? Where you do
First outside, inside last.
Okay.
Yes.
So can you guys walk me through this, what this would read?
X squared plus h squared?
X squared plus, if you do, I'll write this out
Oh,
here so
yeah,
you guys
I
can see
did
a
it
visual.
wrong.
X squared plus
XH
X.
plus,
HX.
well wait, you
Same
can say
way.
that. So
Yeah,
it'd be
XH.
2xh
There we go. H squared.
plus h squared. So that's just that one minus this one,
X squared.
all over.
H
Okay. Can you see any terms that cancel out each other?
squared.
Yep. So cancel those out. And you now have 2xh plus h all over x. This is where the concept of the derivative comes in. As h equals 0. Now, after we've gotten this far, you let h equal 0. So if h equals 0, what are you left with?
2x.
2x.
Over 0.
And that is the derivative of f of x.
Yeah, buddy.
Yeah, buddy. So, very good. And there actually is a shortcut for this. But would you guys like to do another example on your own?